Hi, my name's Zach Hershen.
And I'm Ben Greenspan, and the question we're going to be investigating today is how does a body in two-dimensional motion react when it hits water, and how does rotational velocity of a human change when their radius changes? So we're going to watch the video that we created to investigate this.
As you can see, I jump up, do a flip, and then strike the water and stop. So, the first component of our analysis will be the x velocity. As you can see here is the data table logging all the points, the x and y position, and the x velocity. As we move down here to the x velocity versus time graph, as we move down here to this graph, you can see that from 0 seconds to 1.5 seconds in the video, my hips were being pushed forward to build up momentum for the jump, which registered as a velocity fairly constant around 0.5 meters per second. From there, I proceeded to jump and leave the block at 1.5 seconds, at which point my x velocity was at a maximum because I had maximized my x acceleration and therefore force, resulting in my x velocity being maximized. From there, what shows up on our graph is pretty random and scattered points, but that was due to the level of imprecision when we were recording the data in the video point computer program. What should happen is a gradual decrease in x velocity due to air resistance until it ultimately reaches zero upon collision with the water.
The next thing we're going to be discussing is the y velocity. So right here is the data points for our y velocity, first of all. And then right here, underneath, is our y velocity versus time graph. So the y velocity is 0 as Zach is crouched down until his body begins to extend upwards around 1.4 seconds, at which point the y velocity increases to a max of 1.3 meters per second at 1.5 seconds. So that's right here. When his feet detach from the block, which is when his feet detach from the block, the y velocity decreases until it reaches 0 meters per second at 1.6 seconds, which is where the maximum height is achieved. From there, the magnitude of the y velocity increases to a maximum of 3.5 meters per second at 1.75 seconds. Just before Zach makes contact with the surface of the water. From there, his y velocity decreases as he enters the water until it reaches 0 meters per second when he comes to rest at 2.3 seconds.
So next up is x acceleration. So as you can see here are the data points. I'll just check through those pretty quick. So now we move to the x acceleration versus time graph. As you can see, for the first approximately 1.4 seconds, the points are fairly erratic, and this was due to the center of mass of myself moving fairly erratically during the first 1.4 seconds of the video as I prepared myself to jump up. Then the acceleration spikes up between 1.4 and 1.5 seconds, which is consistent with our data, as I extend my legs and ultimately leave contact with the block at 1.5 seconds, which is where my acceleration reaches a maximum. Then, as soon as my feet leave the block at 1.5 seconds, there's a dramatic drop-off in acceleration on the graph. What should actually happen, in theory, is that the acceleration should go to 0, because in two-dimensional motion, x velocity remains constant, because as soon as I leave contact with the block, I no longer have a force propelling me forward. I'm not accelerating in the x direction, so my acceleration should be 0. However, that is not the case due to issues with software and imprecision when plotting the points.
next is the y acceleration. So here's the data points in our table. You can take a little look at that. So here's the graph of y acceleration versus time. So our graph is a little bit crazy over here because it was hard to get data points. What should actually happen is there's a positive y acceleration from the point where he's crouched down to the point where he leaves the block, which is about like this part right here. And then after this point, he should experience a negative acceleration of 9.81 meters per second squared in the y direction, which is what should happen from in this general area, but it was kind of off again because of difficulties with taking data.
And for the final analysis, we are going to analyze the angular velocity. So the equation for involving angular velocity is v equals r omega, or linear velocity equals radius times angular velocity. Therefore, angular velocity is equal to linear velocity divided by the radius. Therefore, as radius decreases, angular velocity should increase. So, in the video, as I jump up and begin to tuck myself into a ball, my radius decreases, which results in my angular velocity increasing. However, it will remain constant, or fairly constant, until the time when I begin to extend from my tucked position, at which point my angular velocity will decrease as my radius increases. This is why, if you have ever tried to do a flip in a straight position, if you were to try to jump up and just flip over, staying straight, it'd be a lot harder because your angular velocity would be slower because your radius would be larger.
So next we have a couple of free body diagrams that Zach's going to go over, just about some important points in the motion.
So one such point was the maximum height. At the point where I achieved my maximum height indicated on the y velocity graph when my y velocity was 0. At this point, I am experiencing the force of gravity in the negative y direction and the force of air resistance opposing my motion, so in the negative x direction. Now we're going to head over to the computer and just check out one snapshot of that point in time where I did achieve my maximum height. So as you can see, I have achieved my maximum height. The only forces acting upon me are gravity and air resistance. So next up, we are going to the next point, which is leaving the block. At this point, I was experiencing the force of gravity, of course, and then I was exerting a force backwards behind me, and the normal force was opposing that motion. So we're going to head to that right here. We have this. Why don't we have this? Oh, we have that right here. We have that right here. At which point I am just leaving the block. My legs are fully extended, and I have just exerted a force in this direction so that I'm able to jump in this direction. So, specifically the maximum height graph, that is in agreement with our y velocity graph, because at the point at which I achieve my maximum height, as you can see on the graph, my y velocity is 0 meters per second because I have achieved my maximum height, and I am no longer, at that instant in time, I do not have a positive or negative y velocity, just a negative acceleration in the y direction. Also, when my acceleration when I'm leaving the block, that is in agreement because my y velocity increases drastically from 1.4 seconds to 1.5 seconds, which is when I have my legs crouched and am extending them as I prepare to jump. On all 4 graphs, actually, it is very clear that I am accelerating, specifically y velocity, x velocity. My velocity spikes up from 1.4 to 1.5 seconds, and right here, 1.4 to 1.5 seconds. So,
thank you very much for watching this video.
We hope it's been enlightening. I never realized how much really went into doing a flip. But yeah, hope you have a nice day, and see ya.